This video covers chapter 23 of the Higher GCSE books, and this is to do with graphs. So the first bit we're going to look at is going to be, actually we're going to do some bits together, distance time graphs here and velocity time graphs. So these bits we'll do together. So we'll have a look at this and these two bits here, and then that'll be done. Okay, so let's first of all start with a distance time graph. So we would have come across these before. So we have time along this axis and distance on this axis. So we may or may not have a straight lines here. So we've done this type of thing before where maybe we've had a graph like this. We know that if it's flat, the object isn't moving, it's stationary. And with these lines here, the steeper it is, the faster the speed. So steeper equals faster. And in fact, on these graphs, the gradient of this graph equals the velocity or speed. Okay, so to find a gradient, what we do is we look at the rise, how much it changes by going up or down, divided by how much it goes across, the rise divided by the run. And on this, that's going to be the distance, because that's on the y-axis, divided by the time, and that fits with the equation for speed, distance and time. Yeah, and speed equals distance divided by time, which is what we expect from the formula. Now if we compare this to a velocity time graph, okay, so time along on this axis, but not distance but velocity, then if I have a similar type of graph like this, then when something is flat, it actually doesn't mean it's stationary, it means it's moving at a constant speed or constant velocity. So it's a bit like the cruise control on a car, it's moving at a constant speed. Here, steeper actually means faster, or an increase, or faster acceleration. So it doesn't mean a faster speed or faster velocity. Let's put that there. In this one it means a faster acceleration, and in the previous one where we had the gradient is the velocity, here the gradient equals acceleration. So the gradient equals acceleration or deceleration if the gradient is going down. So there are some similarities, there are some differences. So just like before, if you want to find a gradient, we would do the rise over the run. In this case the rise is going to be the velocity. Don't know why I put rune there. It's the run. It'll be the velocity divided by time. So the velocity divided by time gives you the acceleration. So that covers the distance time graphs and the we've done that bit there. So now we're going to be looking at the bit where it says the area under a distance time graph. Now the area under a distance time graph on this one, for example, is going to be this. yeah, sorry, not a distance time graph, a velocity time graph, that area is equal to the distance travelled, or the distance covered. So if we can calculate that area, what we've got is the distance that something has travelled, so that's important. Now, on the one that I've got at the moment, this example, that area shouldn't be too difficult to work out, because we can divide it up into, say, like a triangle, a couple of triangles and a trapezium and a rectangle. So when it's a shape like that, it's easy to work out. But if we have, let's say, a velocity time graph, so I'll just put V here and T, and it's not something that we can easily work out the area of. So if I wanted to, let's say, calculate this area like that, and I want to find that area to find the distance travelled, the way that we do it is we split it up into strips like this, equal size strips, and we basically make them into like little trapeziums like this. So we join the tops together and we would estimate the area. So in a velocity time graph like this, where it's not straight lines, we would estimate the area by dividing the area into strips, which are trapeziums or trapezia, yeah, which is the plural for trapezium, yeah. And so each one of these little, let's take one of them, let's say take this one here. Okay, so that's basically a trapezium on its side, so it's going to look something like this. So what I would do is, this would be A and B, yeah, and I can just read that off from the Y velocity axis, and this would be H, the height. Okay, so it's a trapezia that's on its side, yeah, as you can see here. Now, depending on the shape of the graph, when we estimate the area, we could end up with an overestimate or an underestimate. So let's see when we get an overestimate or an underestimate. So I'm going to draw two types. So let's draw one that goes like this, and let's say we drew one that went like this, and I wanted to estimate the area, and I do that because I want to find the distance travelled. So let's say I split it up into strips like this, all equally sized. Normally in the exam they would expect you to divide it up into 4 strips, 4 or 5, a minimum of 4. Now if I join the tops of these up, I'll do them in a different colour. So this blue line here represents the tops of those trapeziums here. This blue line represents the tops of the trapeziums. In the top graph, in this graph here, my estimate when I work out these areas here would be an underestimate, because can you see the tops of the trapeziums are below the actual graph line? Okay, so when I estimate my area, my estimate is an underestimate. The reason being the ends of the trapezia are below the curve. we're trying to measure. Whereas if I was trying to find this area here as an estimate, you can see that the ends of the trapezia are above the curve, so my estimate here would be an over estimate, yeah, for similar reason as before. And the reason it's over estimate, the ends of the trapezia are above the curve that we're trying to estimate the area of. So remember, when we're calculating this area, what we're doing is we're finding the distance travelled. That's why we're working out this area and estimating it when it's like this curved shape. Right, so we've done the distance time, velocity time and estimating. We're now going to move on to filling containers. So filling containers, and what we need to do is basically match up containers with graphs that show the height of the liquid in that container as it's being filled. So it may be a container that looks like this, that's wide at the bottom, becomes narrow at the top. It may be a container that maybe just goes straight up like that as we fill it. It may be a container that's sort of rounded one like this. Yeah, all different shapes in container. It may be one that changes from one shape to another like this. And we need to be able to draw the filling graphs. What does the height look like as it's being filled? Now, what we just need to remember is that if the container is wide, then on the graph, the line or the curve will go up. It won't be steep. So wide equals less steep, whereas narrow means more steep. Okay, or a greater gradient. So narrow means more steep. So let's draw underneath the graphs for each one of these. Yeah, so time is going to go along the bottom, height is at the side, so the height of water in that container. Yeah, and sometimes you need to draw it. Most of the time it's going to be some containers are drawn, and you need to match up the container with the graph. So if I start with the first container, can you see it starts off wide and it gets narrow. So what that means is the graph is going to start off, and they all start off in a bottom corner. It's going to start off being less steep and it's going to get steeper. So probably something like that. Okay. The second one, it's the same width all the way up, so the gradient doesn't change, so its height will just go straight up like that. Now the third one, I haven't drawn it very well, sort of gets wider and then gets narrower, so it's going to get steeper but then become less steep. So I'll have maybe something like that. Oh sorry, no, it'll be the other way around, won't it? It gets wider and then it gets narrower, so it gets less steep, so probably something like this, and then it gets more steep, so something like that. Now the last one, it's sort of the first part of the container sort of goes out like that, it's not changing width, then all of a sudden it jumps and gets thin. That means the gradient's going to all of a sudden jump and look like this. But if you can remember, wide is less steep, narrow is more steep, that will help you match up containers to their graphs. Right, so let's move on to the next topic here, which is recognizing different types of graphs. So an x and a y axis. So we should already be able to recognize the graph of x squared. We know it's like a U shape or a N shape. Graph of x cubed will look something like that. Okay, so this is the graph of y equals x cubed. So that's that first one here. Next type of graph, the graph of 1 over x. It's a strange looking graph, it has these gaps in it. So the graph of 1 over x looks like this. And these bits that I've drawn actually go on forever, but I've only drawn bits of it. So this is y equals 1 over x. Then the last graph there that it says we need to recognise is the graph of y equals a to the x. Now this is something that starts to sort of go up like this. Now all of these graphs cross at the number 1. But yeah, y equals a to the x. So often these questions are match the graph up with the equation of the graph. Next is this topic here, transformations of graphs. So basically in these questions you're normally given a graph, okay, and it's called y equals f of x. We're not given the equation, we're just told this is what the starting graph is. And you need to do some stuff to this graph. It maybe you move it up or down, you reflect it in either the x or y axis, and we're going to recognize each type. The first type is if you see this y equals f of x, so that's like the original graph, plus a. So whenever I write a here, it can be any number that goes there. What this means you do is you move the graph up by the number. So move the whole original graph up, whatever graph's been drawn in the question, move the original graph up by a, whatever that number is. Now if a is negative, it will move down. So to summarize, it's basically a plus a will move it up, negative a will move it down. So if you see y equals f of x and you see plus a on the end, plus some sort of number, it will move the graph up or down. The next type is, let's take that out of the way, y equals f and then x plus a. Now what this will do, it will either move the whole graph to the left or the right. So what this will do, it will move the original graph to the left by a. So whatever that number a is, the graph will move to the left by a. Now if a is negative, it will move to the right. So to summarize, if we have plus a, and I should have put plus a here in that previous one, if we have plus a here, it moves that way. If we have negative a, it moves that way, and the whole graph will move in that direction. Next, the next two are reflections, so they will reflect the graph. So if I have y equals negative in front of the whatever the graph that's given, the f of x, what this does, it reflects the original graph in the x-axis. Okay, so reflects the original graph in the x-axis. That's basically your mirror line. So basically what happens is the graph gets reflected around the x-axis that way. So there would be my x-axis like that, and you just reflect the graph in that mirror line. Then the last type is if we have y equals f and then in brackets negative x. This reflects the original graph in the y-axis, so reflects the original graph in the y-axis. So that will reflect a graph around this way. So here's my y-axis there. So basically that becomes our mirror line. Yeah. So I suppose I could write down here x-axis is mirror line, reflecting, and here y-axis is mirror line. So we need to know those different 4 transformations, and maybe if a graph is given and something's happened to it, we should be able to work out which of the transformations it is. And also don't forget about coordinates. If any coordinates are given, what you need to do is to work out what those new coordinates are. So for example, if it's the first type of transformation, then the y coordinates are going to get changed as the graph gets moved up or down. If it's the second type, the x coordinates are going to change as it gets moved left or right. In the third one here, what's going to happen is the y coordinates will flip from being at the top to the bottom. And in the last one, it will be the x coordinates that flip from one side to the other. So any positive x coordinates will become negative and vice versa. Last topic here is to do with the equation of a circle. So equation of a circle. Now the equation of a circle, these will be circles where the center of the circle is at the origin. So it's going to be a circle something like this, and the equation of a circle is x squared plus y squared equals r squared, where r is the radius. So the radius of the circle would be r. So e.g., if I had the equation of a circle which was x squared plus y squared equals 36, I know that on my coordinate grid I need to draw a circle that has a radius of 6. So I could probably put those coordinates on like this and put 6's here, 6 there, 6 here, negative 6 here, negative 6 here. And knowing what we know about straight lines, we should be able to find the equation of a tangent to a circle. So for example, if I had a tangent to a circle here and I want to find the equation of that line, what I would do is I would find the equation of this, or find a gradient of the tangent or this radius. So we'd start by finding a gradient of that, and we should be able to find it because we might be told what this coordinate is here. Yeah, and then we can use that to find a gradient of that. Then we're going to do minus 1 over m, and m is this gradient here, to find the gradient of the tangent. Gradient of tangent. And then we can use y equals mx plus c to find the equation of that tangent, because m we would have just found, and then we substitute in x and y, that's this coordinate here, and then we can use that to find c. So maybe I'll put this coordinate equals x, y, and that's chapter 23 complete.